Continuing our journey with real numbers, how do we represent them? As I mentioned yesterday, all real numbers can be placed on the real number line. If it's been placed on there, it's a real number line, and can be described in different ways. Geometrically, we could actually draw the number line and place it on there. We could have a picture. Algebraically, could be an equation, or an equation could tell us what's happening with these numbers. Interval notation. Often when we talk about domain and range of functions and relations, we use it there. Set notation, so the formal language of maths. Different types of intervals then, speaking of interval notation. An interval could be bounded, so it has boundaries, it has endpoints. It could therefore also be unbounded. It might only have one endpoint and the other one just keeps going. So an interval could be closed. So if those endpoints are included in the interval, then we say it's closed. Or it could be open if it's got an endpoint that's not included. And then there's this fifth one, which is a single point, and it gets the wonderful name of degenerate. So a single point is a degenerate. Let's have a look at some of these. X is greater than 5, so it is written as an inequality. On the number line, I would draw it like that. Now, a couple of things to note here when I'm doing it. My arrow, I don't put on the number line. I'll always put it slightly above, because I think if you put it on the number line, you can lose it. It gets lost in the line itself, depending on what colour ink you're using and things like that. So I just find it a lot easier to have it just slightly above the line to make it clear. Yeah, I'm talking about all the numbers in this direction. The open circle tells us that 5's not actually included. That is open, it's unbounded as well. So it met the criteria for open and unbounded. Interval notation, we would write it like this. The parentheses indicate that the endpoint is not included. So that's where we use parentheses. We're starting at 5 and we're just going. So we're going all the way up to infinity. And of course you can't include infinity because you never get there. So we have a parenthesis on the right hand side there as well. Or parenthesis would be singular, wouldn't it? Parenthesis. In set notation, now I've written it as a describing set. So it's X, the colon in set notation basically means such that. So we've got all the X's such that X is greater than 5. X is greater than 5. Less than or equal to, very similar one, but now we colour in the circle to indicate that, hey, this endpoint is included. So that one would be a closed unbounded interval. And when it's closed, we use a bracket rather than a parenthesis. And there it is in set notation, X such that X is less than or equal to 6. Okay. Oh, we got 2 points now. X is in between 4 and 6, but both of them are not included. So that one would now be bounded. It has 2 endpoints. It's also open because those endpoints are not included. And so it looks like we're writing down coordinates with this one, 4, 6, but no, we're talking about the interval that goes between 4 and 6. So X such that it's in between 4 and 6. And let's do one where the endpoints are included. That's a closed bounded interval. And there it is in its different notations. Which brings us to something like this, where one endpoint is included and one is not. So what do we call this? Well, it's simply bounded. We don't say open or closed because what is it? One side's open, one side's closed. It's just a bounded interval. And there it is in its different notations. Okay, let's talk a bit more about rational numbers. And rational numbers, we said, were numbers that can be in the form of A over B, where A and B are integers. Now that includes whole numbers, of course, because B could be 1. Probably more interested in irrational numbers, which then are the ones that are not rational. Now, talking about decimals, every irrational number can be expressed as a unique infinite decimal. We talked about terminating decimals and we talked about recurring decimals. They can be written as fractions. But these infinite ones cannot, if they're not recurring. Pi, of course, is our classic one, and just off the top of my head, pi is about 3.14159927932844197816499375102817494459230781640628 approximately. Mind you, pi, of course, is not my favourite irrational number. I'm sure you all have your own favourite irrational numbers. Mine's phi, not pi. Phi is much more interesting. That's all to do with the golden ratio and what have you. 1.619. There you go, that one I could do. We're going to prove that the square root of 2 is indeed irrational. I'm going to use a method called proof by contradiction. And proof by contradiction is actually where you assume the opposite of what it is you're trying to prove. So I want to prove the square root of 2 is irrational. I'm going to assume it's actually a rational number. So I'll define it. The square root of 2 is a on b, but I need to define what a and b are. And whenever we have a proof, we reserve the right-hand side for our explanations and things like that. So I'm saying, well, look, a and b are going to be integers with no common factors. That's what I'm saying. They're going to be integers with no common factors. Another way of saying that is they are co-prime. Co-prime are numbers that have no common factor. So co-prime. Well, that means b root 2 is equal to a. All right? If I square both sides, 2b squared would be a squared. Everything's good so far. So I know a squared is divisible by 2 because I've defined b to be an integer. So I know I've broken it down into factors that are integers, 2, b and b. Okay, so it is divisible by 2. But hang on a sec. If we're talking about squares, prime factors will always appear in pairs because you're multiplying a number by itself. So you'll always see the number there at least twice, but it'll always be an even number of times. So that means that any square that's divisible by 2 must also be divisible by 4, because that factor of 2 will appear there twice. So a squared must be divisible by 4. That means 2b squared, because we said 2b squared was a squared. That means 2b squared is equal to 4k, which means b squared is equal to 2k. Hang on, a squared was equal to 2b squared. B squared is equal to 2k. Well, they've both got a factor of 2. That means they've got a common factor. But I started off by saying they have no common factor. There's my contradiction. I've got a situation which is impossible. They can't both have a common factor and not have a common factor. That doesn't make sense. So A and B don't have common factors, so the square root of 2 is not a rational number, because my proof has just fallen over. I've got a contradiction. So, well, if it's not rational, the only conclusion that I can draw is, well, it must be irrational then. So if it's not rational, it's got to be irrational. And there's my proof. Let's talk about these things called significant figures. Our irrational numbers, we can't work them out exactly. Now, sometimes an approximation is going to be required, certainly in science, because they have problems when we say, what's the area of this shape? And we'll say, oh, well, look, it's 4 pi. Now, we're happy with that. Pi is an exact number, but in science they're not. They would like us to round off, and they often use significant figures. So when approximating a number, we could write it to a certain number of decimal places. That's usually the easiest way of doing it. However, in science, that's probably not the best way of doing it. Significant figures is probably a better way of doing it. So we would prefer a certain number of significant figures in scientific things. How do you round off? Well, it's exactly the same. But the only difference is, instead of starting at the decimal point, you start at the first non-zero digit and then count the required number. So, here we go. If I had to round this to 2 significant figures, instead of starting at the decimal point, I'd start at 5. So I go 5, 0, the next number's 7, round up, 0.051. If I was to do it to 3, then I'd go, oh, well, 507, the next number's 0, round down, 507. 4 significant figures, 0, 5, 0, 7, 0. Okay, now that's the thing with significant figures. Unlike rounding off to decimal places, we include the 0 at the end of the number if it turns out that that number is 0, because it becomes significant. 3,000 to 2 significant figures. This one's interesting. Okay, so we go 3, 0, next one 0. Oh, so it's 3,000. To 3 significant figures. Oh, 3, 0, 0. So oh, it's 3,000. To 4 significant figures. 3, 0, 0. Oh, it's 3,000. They're all the same. That's why we have scientific notation. Because when you're talking about whole numbers like that, it's really hard to tell how many significant figures it has. But if it's in scientific notation, you can express it so you can let people know exactly how many significant figures it has. So if it is ambiguous, like these last 3, that's when you should use scientific notation if you're talking about significant figures. And they would be the answers in significant figures. And now we can see the difference and we can see the significance of each of those numbers. So how do you then find the number of significant figures? Well, again, start at the first non-zero digit and just count to the end of the number. So there's 0.05073. Well, there's 5 significant figures. 0.010. Doesn't matter. All these zeros that are in between there, they're there for a reason. They're significant. So that has 5. Here, again, this 0 at the end is significant. Why put it there? They're telling us something. It may have been we measured something and it just happened to fall exactly on the line. So that last one was 0. Whoa, hang on. Start at the first non-zero. Well, we know this could have 2, this could have 3, or it could have 4. So what answer do I put down? Well, I'll put down 4. Okay? I'll always go with the largest one. I might not be right, but I can't be wrong. I might not be right, but I can't be wrong. Now, unless they give me more information, I don't know. Is it 2, 3 or 4? Someone's going to go with the biggest one, unless they give me more information. So yeah, I'm going to put down 4 significant figures for that one. We're going to do now the Shakespeare exercise. Or are we?